Sorry about that, guys. My camera screen recorder only has about 10 minutes in it before you have to stop because it's not a paid, I don't have the paid for version. So, picking up from where we left off in Dijkstra's algorithm, the only thing I was really going to say was that you're not actually technically done with the algorithm till everything in the known column is marked as true. So technically you still have this one, you have C to finish, and you have A to finish. And then you're totally done with the algorithm. So with that in mind, we're going to do another algorithm, or another graph, and we're going to try and figure out 2 cycles worth of it. Now here's the tricky part. What's happened is the teacher has been a little sneaky, and he's already done the first part of the graph for you. Note that true's been updated on several of these, and multiple distances and parents have been figured out already. So what you have to do is you have to logic this out for a second. You have to say, okay, which one of these was its clear root? Where was the starting point of that? That's very easy to look at because it'll be the distance of 0. So clearly the starting point was A, and then he scanned and found the lowest, which was B or F, and he updated accordingly. So it really doesn't matter. All you have to do is follow the algorithm. It really doesn't matter where he starts you in the algorithm. It should be very simple to do. Just start as you know how. Look at the distance column and say, what's the lowest? That's false. Okay, the lowest that's false is going to be 9, it looks like. So we know to immediately jump to G and set that as true and start here. So with that in mind, I'm going to go through this sort of at a quicker speed to get a real idea as to what you can do in real life and how quick this can work. So G is true. So if G is true, we look at it and we say G is 9, so 9 plus 1 for F. Actually, F doesn't matter because F is true. Have we been to E already? E we've been to at a cost of 15. So is 9 plus 10, 11, 12, is 12 less than 15? Yes, it is. So this is 12, and we update the parent to be G, and we check that out. So has H been updated yet? No, H has not been, so 9 plus 2 is 11. And 11 is less than infinity. And the parent would be G. So this is the first table. Let's do another table going off the same example. Let's bring the table down here. We look for the lowest in the distance column. We say, okay, the lowest is that's false, that is. The lowest is looks like 11. Yep. Okay, so 11 from H. So we go up to H and we look at it and we say 11, we can get to C and we can get to Z. We already know we've hit G. So we look at C and Z. It turns out both C and Z are false, so we can look at either one of them. So H currently has 11 associated with it, so 11 plus 10 can get us to Z, so a cost of 21. 21 is less than infinity, so we know that we can get there from H at a pretty low cost of 21. Well, low is relative, I guess. And we can go up and we say, let's see, H again was 11, so 11 plus 4 is 15, and 15 is currently not less than what's at C. So we do not update C. And we'll do one last one, just to really, really hammer this home. We update the table by looking at the distance column, and we say, okay, what is the lowest value in the distance column that's also true, or that's also false? Well, we've got 11, 21, infinity, 12, 12, and that's it. Now it looks like we've got a tie here between E and B. The way to solve, or I'm sorry, E and C. The way to solve this is lexigraphically. It really doesn't matter as long as you're consistent. But you can pick lexicographically if you want. So I'd go C because C goes before E in the alphabet. So let's look at C and mark it as true. Go up, and we know 12 is the value associated with C currently. That's the cost. So 12 plus 8 is 20, and that can get us to B. So is 20 less than whatever's at B? Oh, turns out B's marked true, so we don't even care. Is E, H, or D also marked true? Let's look at it, and it turns out E is not, H is not, and what was the other one? Z? Z is not. Okay, so the other ones have values associated with it. So we look at it and we say, okay, from C, we know C is 12, and 12 plus 2 will get us to E. So 14 at E. Is 14 less than whatever's here? No, it's not, so we don't update. So 12 plus 4 is 16. Is 16 less than whatever's at H? No, it's not. We don't update. Lastly, we look at D. Is 12 less than 7? Oh, I'm sorry. Is 12 plus 7 less than whatever's at D? So is 19 less than whatever's at D? Turns out, yes, it is. 19 is less than infinity. So we update D, and we make the parent C. Now again, this isn't actually technically done until you're totally done with marking everything true, and then you have the shortest path. Now, lastly, I want you to just go through on this very last example and try and solve this yourself. Try and solve this entire problem. Now, the only thing I've done is I've done something a little sneaky. I've added arrows, and these arrows are going to be sort of markers, and this means it's a directional graph, which means you can only go to places that obviously the arrow's pointing. So 4 can get to 3, but 3 cannot get to 4. So go ahead, try and solve this yourself, and I'll be back in a minute. Alright guys, hope you figured it out. I did 3 tables, but then I also went through and finished it because I want to show you something else. But these are the 3 tables that I asked you to do here. So starting at 4, we found Dijkstra's algorithm to find everything else, or use Dijkstra's algorithm to find the shortest path to any other node. Now I want to show you why this is applicable. At the very end, I'll show you how to use these tables to find it for anything. So let's say I'm starting at 4, and I want to find the fastest path to get to, let's say, 3. Okay, it turns out 3, well, 3 is not a good example. Let's use fastest path to get to 6. Well, it really doesn't matter. Basically, all we're going to do is we're going to start, and we're going to say, what vertex do we want to find? Let's look at vertex. We'll go to the last thing, because this is the table we'll be looking at. We're going to go to this guy, which this should be marked as true. And we should look at it and we should say vertex 7 is what we want to get to, starting at 4. What is the quickest way we can get there? Well, it turns out the quickest way will be a cost of 6. So the cost is going to be 6, and the path is going to be, we're going to go to 4. You can see right here, this is 4. And that's the only path right there. It turns out we can directly get from 4 to 6 at a cost of 6. So if we go up and look at this, fix that. We can go directly from 4 to 6, or I'm sorry, I'm saying 6, but I mean 7. 4 to 7 at a cost of 6. So another example would be, let's look at trying to get to 2. We can get to 2 with a cost of 6 from, well, the cost will be 6, so we start at 1, and then we go and we look from 1, we go to 1, and we know that we have to go to 3. And we go to 3, and from 3, we go to 4. So 1, 3, 4 is the path we use to get there for a cost of 6. So going up 1, 3, 4, we obviously have to flip the path. So 4 goes to 3, and 3 goes to 1, and that's a cost of 4. Just like that. 1, 3, 4. So that's going to be the total path, and it's going to end up costing 6 total. So hopefully that makes sense to you. Yeah, that should be good. So if you guys have any questions, feel free to give me a shout out, and just leave a comment on YouTube. Thanks for your time.